Greetings, everyone. The purpose of this video is to go over an application problem that could be modeled using quadratic functions, and to also kind of show why a quadratic is a good representation for the situation that we're looking at. So the problem you'll see here on the slide that we're given is that the altitude in feet of an arrow t seconds after being fired is given by the equation a of t equals negative 4.9 t squared plus 34.3 t plus 6. And notice a couple of things looking at the equation. So first of all, we're told that we're measuring time in seconds and that it's represented by the variable t. So we know in our equation here, the variable t stands for time. And then we're looking at altitude as a function of time. And so since our function is written as a of t, the variable a here is representing the altitude. And I point that out because that'll be important as we go through this problem. Okay, and then you'll see here we are asked to calculate 4 different values related to this situation. So the first being from what height was the arrow fired, second being how many seconds does it take for the arrow to reach its maximum height, then what is that max height, and then finally how much time does it take for the arrow to hit the ground. Now, before we actually go ahead and calculate those values, I first want to look at why a quadratic can be used to model this situation. So if you'll humor me for a minute and allow me to make a drawing here, but not with that tool. So I'm going to do my best to draw an arrow here. So that's an arrow. And if you can imagine an arrow being shot into the air, it would do something like this, or its path would look something like that. And if you notice, that looks an awful lot like an upside down parabola, which then gives us some evidence that probably a quadratic would be a good way to model this situation. And in fact, we see that this function here, in addition to being a quadratic, notice that the leading coefficient, the one next to the t squared, is negative, which tells us the graph is going to look something like this. It will be an upside down parabola. Okay, so it'll kind of match that shape of the arrow's path. So what I'm going to do is I'm going to go ahead and sketch the graph here. And when I say sketch, it means it's going to be very rough, or a bit of an estimation of what the graph would look like. It's an upside down parabola, so I know it's going to do something like this. Okay, and maybe let me try to redraw that. Yeah, that's a little better. Okay. And a couple of additional things then I want to say now that we have the graph drawn. So first of all, in our function, as I just pointed out on the previous slide, our input variable is t, the time, and then our output variable is a, the altitude, which means that in our graph here, the values along the horizontal axis, the input axis, those are going to be values for t, okay, for the time. So the numbers that we see there will represent times. And then on the vertical axis, those are going to be the values for a, or the altitude, okay? And that'll be really important as we go through this problem. All right, the other important things I want to point out here on a graph of a quadratic. We know, first of all, that there is always the vertex up there, which we represent with the coordinates h and k. There are horizontal intercepts, so these points here and here, which have the form number, comma, 0. And then we also see in this quadratic a vertical intercept, which we recall vertical intercepts have the points 0, comma, number. And I point those out because as we go through those 4 values that we were asked to calculate in the problem, each one of those is represented by one of these 4 points that I've pointed out here. So as we go along, we'll need to, in order to calculate each value we're asked to calculate, we have to figure out which of these points it corresponds to. Okay, so let's look at the first one, which is the point or the height that the arrow is fired. I'm again going to draw a little bit of a smaller version of our graph here as a reference. Okay, so it looks something like that. And again, we have those 4 points, the horizontal intercepts, the vertex, and the vertical intercept. I'm going to figure out, if we're talking about the height that the arrow was fired from, which of those points would we be talking about? Well, one thing to think about is that if the arrow is fired, right, or we're looking at the height where it's fired, when it's initially fired, that happens at the beginning of when the arrow is shot into the air. And we know that that process is going to start, or maybe it's like right before it starts, at time t equals 0. And if you remember over here on our graph, right, the horizontal axis, the values along there represent values of time, or t, and then the vertical axis represents values of the altitude, or the height, or the values of a. And if I look at those 4 points there, and keep in mind this fact that when the arrow is fired, it's at t equals 0. The only one of those 4 that will have t equals 0 is this one right here, because remember that's the vertical intercept and it has the form 0, comma, number. So this tells me that in order to figure out the height that the arrow is fired from, I need to find the vertical intercept. And the way I do that is, since my input value is 0, I'm simply going to plug in 0 for the value of t. So we're going to do a of 0. And then since 0 takes the place of t, we plug it in everywhere in the function that we see t. Okay, and since we have 0 times some values, we know that those will essentially become 0. And so we find that a of 0 equals 6. Okay, and so our vertical intercept is at the point 0, comma 6. And again, thinking about what each of the input and output values represent in this problem, we know the inputs represent time, the outputs represent altitude. And so this is telling us at time 0, the altitude is 6 feet. And so that will be our height, since 6 feet is a height, that'll be our height when the arrow is fired, 6 feet. Okay. All right, so the next two I'm going to group together. So after how many seconds does the arrow reach its max height, and what is the max height, since those two are related. We want to again go to our graph here. Keep this visual in mind as we're going through this. So here's this. I'm going to label our axes. This is A, that's not A. This is T, and this is A. And then we have all of our points. So again, our horizontal intercepts, our vertex, and our vertical intercept. Now we already used the vertical intercept, so it's probably not going to help us on any of the remaining problems, but I'll label it there just in case. And we again want to decide which of these points here is going to help us find when the arrow reaches its maximum height and what that height is. Well, it probably comes as no surprise that the point we're going to use is this one here, the vertex, the one that has that form h comma k. And hopefully you can see that for no other reason than that is the highest point on the graph, right? So it would make sense that that's going to correspond to when the max height is. And again, if you also think about the path of the arrow, right, it does something like this dotted red line. And again, here is where it's at its maximum height. Okay, so we need to find the values of h and k, and hopefully recall that to find those, we start with finding h. We use the formula negative b over 2a. And the values a and b will come from the equation up here. So this negative 4.9, that's the a. The 34.3 is the b. And I should point out, it just occurred to me that this a and this a are not the same thing. They represent different things. the A with the negative 4.9. That's just one of those standard letters we use to represent parts of quadratics. So we'll go ahead and plug that information in here to where it goes. So we'll have the negative of the 34.3 over 2 times the value for A, which is the negative 4.9. And then we will carefully plug that into the calculator, and you can check me with your favorite calculator that the value we get there is 3.5. Okay. So that's that, and then now we need to find the value for K. And remember that K comes from, it's the output value for the input H, right? And since we've already found our input value, 3.5, the way we find the related output value is to just plug that input value into the function. So using our formula from up above, we're going to do A of 3.5. Okay, which means, again, in our equation up there, everywhere we see t, we replace it with 3.5. Okay, and you can, again, check me with your own calculator, your favorite calculator, and I believe we get 66.025. Okay, which tells us then that the coordinates of the vertex of this parabola or this function are given as 3.5 comma 66.025. Okay, and now that we have those values, we have to figure out how do they give us the answers to the questions, right? So we're asked, again, after how many seconds does the arrow reach its max height, and what is the max height? And again, want us to return to, in our graph, what the inputs and outputs are. So the inputs are values of t, the outputs are values of a. So we know that in our coordinate point here, 3.5 stands for a t value, or a time value. 66.025 stands for an a value, or an altitude, which tells us that the time at which the arrow reaches its max height is going to be the 3.5, and the height, the max height itself, will be the second value of the 66.025. So after how many seconds does the arrow reach its max height? That would be 3.5 seconds. And then what is that maximum height? The answer there would be 66.025 feet. All right, cruising right along. We got one more here then. So now we need to figure out after how much time does the arrow hit the ground? And you're probably getting the approach here. I'm going to go ahead and draw the picture. Okay, highlight those points that are important. So this one here, this one here, this one here, and this one here. Label our vertices. So these are values of t, these are values of a. And here we're trying to figure out after how much time does the arrow hit the ground. Okay, which at first might be kind of a difficult question to answer, though. If we think about, again, the path of the arrow looking like this, and where in that path it hits the ground, right? That's going to be here. Think about the ground right here, right? When it kind of hits that flat spot. And when I look at the graph up here, that point seems to relate to one of these two, one of these horizontal intercepts here. And let's try to figure out why that is. Well, remember that these have the form number, comma, 0. Okay, and if I write that out over here, and again, think in terms of inputs and outputs, the inputs of this function are values of t, the outputs are values of a, and I see that at a horizontal intercept, the value of a, the altitude, is 0. If we think about it, that makes sense as a point that would represent when we hit the ground, because when you hit the ground, your altitude is 0, right? You are 0 feet off the ground. So in order to answer this question, we need to figure out the value or values of t, where the altitude is 0, which means that we're trying to figure out values of t that'll make our output up here in our function equal to 0. And so we can do that by taking the equation and setting it equal to 0. So 0 equals negative 4.9 t squared plus 34.3 t plus 6. And then to solve a quadratic when it's equal to 0 like this, you may recall that we can use a number of different techniques, but the one that will probably make the most sense here is the quadratic formula. So negative b plus or minus b squared minus 4ac all over 2a. And as I mentioned earlier, part of the problem, the values a, b, and c come from the formula. So negative 4.9 is a, or not from the formula, from the equation. 34.3 is b, and 6 is c. So we can plug those values in here. So we have negative of 34.3 plus or minus 34.3 squared minus 4 times negative 4.9 times 6. Let me just put those numbers in here. And then that is all over 2 times the value of a, which is negative 4.9. Okay, and since there is the plus or minus, we need to do this calculation twice. Once with the plus, one with the minus. And again, with your favorite calculator software, you can check me on, I believe we get negative 0.171 and 7.171. 7171, not whatever I just wrote there. Okay, and now that we have that, see, there are 2 answers. However, the arrow is not going to hit the ground twice. So we need to figure out which of these 2 answers to use. And if we think about it, right, since we're looking for time, we can't have a negative answer because that would mean that the arrow hits the ground before it is fired. And so that tells us that the answer we're looking for then is the second one, the positive one. So after how much time does the arrow hit the ground? It hits the ground at t equals 7.17, and in this case, this is seconds. All right, that's it for now. Thank you for watching.